Alright, so here we are starting chapter 4, section 1, identifying linear functions. So we're going to identify a linear function and linear equations, and then we're also going to graph them in real-world situations. Alright, so we've got linear functions, linear equations. Just want to note that the word line is inside of there, and that's because we want to make sure that this is a straight line. So no curves, just one point to the next without in a pattern. So here we are with a linear function example. It's a graph who forms a straight line, so hopefully you can see that it's not going to curve anywhere. The graph represents a function, remember, because of the vertical line test. So no vertical line that I would draw would ever touch the graph twice. You can't draw a line that loops back up, so that's not the definition of a line, of course. The graph represents a function because each domain value is paired with exactly one range value. So when we were talking about domain and range previously, remember that we talked about x's repeating. They're saying each x has its own y because, of course, that would mean that it didn't repeat. Alright. So the first thing we're going to do is identify a linear function by its graph. And, of course, it's actually the easiest one because we're just looking for a straight line. So, it turns out this one, not a straight line. This one, definitely not a straight line. This one looks exactly like what we just had. And then this one over here, as much as it is a vertical line, it's actually a straight line, right? And so that's linear. It's just not a function. Alright, so, interesting part about that, because of course it wouldn't pass the vertical line test, right? Because it is a vertical line, so it would touch it infinite amount of times. So, that's not going to work out so well. So, this one is not a function, but it is linear, which is a possibility. Alright, so if we want to identify linear functions other than by a graph, we can also do it by a table. So what we need to do is look at the list of ordered pairs and look for a constant change, or adding a constant number or subtracting a constant number within our x's and our y's. So as we look at the x table here, you notice that between each one of these, you're adding 1. So negative 2 plus 1 is negative 1, negative 1 plus 1 is 0, 0 plus 1 is 2, and 1 plus 2 is 2. So, 1 plus 1 is 2. So, as we look at this, the first column, again, adds 1 each time. The next column, it's a little bit different. Usually, the first column does add 1 constantly. But if we look at the second column, 7 to get to 4 is down 3. And so all we need to do is verify that every single time after that, it's also down 3. So 4 to 1, yep, that goes down 3. 1 to negative 2, that goes down 3. And negative 2 to negative 5. So, if you're ever looking at this and it starts with negative numbers, a lot of times jumping to the positive numbers is actually easier. So, just kind of a hint there. So, their solution here is saying, in this table, a constant change of plus 1 in x corresponds to a constant change of negative 3 in y, and so these points satisfy a linear function. So, if there's a pattern here and here of just adding or subtracting one number, then the points lie on a line. And of course we could have graphed them to look, but you don't always have a time to graph them. So in that case, sometimes we will be looking at just the table. Alright, so this next one here, we're going to try to identify this one as a linear function, and as you can see, it's already been graphed, and so it isn't. But taking a look at our patterns here, x does have a pattern of plus 1. But y, if you take a closer look, 6 and then to 3 is minus 3. 3 to 2 is minus 1. And so you can already see that they are not the same. And so in that case, we do not have a linear correlation. So in this table, again, just a definition, a constant change of plus 1 in x does not correspond to a constant change in y, and so therefore they don't make a straight line. So, as we can see, no straight line, and so we would say by this table, we're not looking at a linear equation.
No.
So the next one, we're going to get a set of points, which of course just actually makes a table anyway. So tell whether each set of ordered pairs, and of course we'll convert that to a table, satisfies a linear function. You could of course do this if you kind of had a better mental vision than I do, but I tend to need them laid out. So as I look through this, I'm going to write each of the coordinates. So we've got 0, -3, 4, 0, 8, 3, 12, 6, and 16, 9. When you do this and check to see if it's a function, you do want to make sure that your x's are going in an order, either least to greatest or greatest to least, so that you can find that pattern. So taking a look from 0 to 4, from 0 to 4 we add 4, and then we just need to check if that happens every time after that. So adding a 4, yep, adding a 4 from 8 to 12, and adding a 4 again. So our x column makes sense, but now we need to look at our y column. So in our y column, we have -3 to 0, that's +3. 0 to 3, that is also +3. 3 to 6 and 6 to 9, all of those are +3 as well. So, does this satisfy a linear function? Yes, it's a linear function. And we can say x's and y's grow constantly. I know in the previous one they talked about the exact values, but in this case that was the idea. Is it a linear function? And of course I can see if you're doing it this way your work, so you don't need to be that specific. Alright, the last piece here is a actual equation. Okay, so checking out the equation to see if it is actually a linear equation. It's any relationship that can be written in standard form, and standard form is this one here. The interesting part, of course, is that most of you have probably been exposed to mx plus b, which you might feel is the standard form, but technically this is actually the standard form of a linear equation. So, what we're going to notice, of course, is that when there is a linear equation to identify, written in standard form, x and y both have exponents of 1. So that's a big one there. We never actually write those exponents, but technically this is an x to the power of 1 and a y to the power of 1, because we wouldn't necessarily be doubling it or anything like that. They're not multiplied together, so watch out for that. If you see an x and a y being multiplied, that's not linear. And x and y do not appear as denominators, so we definitely can't have it in a denominator. There's no exponents, and there's no radicals, meaning square root kind of signs. So if we see any of those issues, they're definitely not going to be. And then, of course, if we see that it's a power of 1, that is what we want. So let's go ahead and identify a few of these. So taking a look at this one, notice that both of the variables x and y have a power of 1. They're not being multiplied. There's no roots or denominators of any sort. And so in that case, we see a standard form linear equation. In the next one, you see that x and y, again, are to the power of 1. Nothing's being divided or multiplied. And so again, this one is going to be a linear equation. And then the last one here, even though there's a negative by it, they both still have power of 1. Nothing's even being added anymore. And so in that case, we do have functions, linear functions. What's going to happen most of the time is that you are going to actually take the time to write them as y equals. So for instance, in this last one here, if it's y equals that I'm looking for and there's a -1 being multiplied out front, that means that I would want to divide everything by -1 to actually get y equals -5x. As much as standard notation is helpful, when it comes to what we're going to be doing later, identifying slope and such, this is actually the format that we would like, which is called slope-intercept form. Alright. Then we have not linear, and again, those are going to be the issues that we have listed here. So maybe there's multiplication, maybe there's radical signs, weird exponents. So Taking a look at this one, we see x times y multiplied, not good. This one here, we see a power of 3, not good. This one here, we see dividing, not okay. Alright, so those are not linear. They're trying to be linear or look linear, but they aren't. Alright, so then the last one here, we're going to tell whether it's a function, and if so, we would then graph it. So taking a look at what we don't want it to be, remember we don't want an exponent that's anything other than 1, and these are both 1, so that works. We don't have any dividing of the variables. We don't have any roots or weird powers, so in this case we are going to go with this as linear. The best way, again, as I mentioned earlier, to graph an equation is to write it as y equals. So going back to chapter 1, when we rewrote things so that we had one variable on a side and then everything else on the other side, it's best if we rewrite this so that it's y equals. So how do I get the y alone? Well, the plus 4 here is definitely making it so that we can't have a y alone. Remember, we're doing SADMAP here because we're solving, so we're going to identify any addition and subtraction that we see. So there it is, and we're going to undo it. So we now have x minus 4, and then that's going to equal 2y. After our addition and subtraction, we look for division and multiplication. Definitely going to be multiplied by 2 here, so we divide 2 to everything. Once we divide by 2, we do have y all by itself, which is what we want, and then we're going to have to simplify a little bit. We have talked about this, but I just want to make sure that we understand that this is technically dividing everything, including this 1x, by 2. So if we divide every piece by 2, you'll notice that we're actually going to get 1 over 2, so 0.5x, minus 4 over 2, so minus 2. This will make it a lot easier to put it into a table, because all we need to do, as we've seen before, is kind of center around that 0, so negative 3, negative 2, negative 1, and plug in each of these for the x in order to get the y. So what I'm going to do is put in my first value, which is 3, negative 3, and so I'm going to do 0.5 times negative 3, and then to that, subtract 2. So 0.5 times negative 3 is going to give me negative 1.5, and then minus 2 is going to give me negative 3.5. The next thing I'm going to do is plug in a negative 2. So we have 0.5 times negative 2, which is negative 1, and negative 1 minus 2 leaves us with negative 3. Next one that we're going to plug in is negative 1. So negative 1 times 0.5 is negative 0.5, minus 2 is negative 2.5. Hopefully you can see that as I'm filling in this chart, I have a pattern of adding 1 each time, which we talked about with our table. And in the right side here, we actually have a pattern as well. It's harder, again, like I said, with negatives, but you are actually adding 0.5 each time. Just a side note, as we look at what we're doing here, this is our 0.5. We'll talk about that in a little bit. So I can actually figure out that the next one of this is going to be negative 2. After that, I'm going to add 0.5 again and get negative 1.5. Add 0.5 again and get negative 1. And then add it again and get negative 0.5. So as I look for a graph of this, I go over 3 and down 3.5. Then I go over 2 and down 3. Over 1, down 2.5. And so on, going up a half each time. Of course, this does make a linear line, a very straight line, going through those, especially if I could draw it on this device. So that's graphing. So the idea is that we have linear equations. We know how to identify them with a table, with a list of points, with an image of a graph, and then also with a function, which is going to be this equation that would be given. Alright, so that is Chapter 4, Section 1, and hopefully you can apply that to our assignment.